Hello, this is Professor Elliott, and in this lesson we will look at flip-flops and latches. All right. Okay, so there we go. Okay, so the SR flip-flop is sometimes called SC. So the terms S stands for set, and when we set a flip-flop, we're making its output, and the output is called Q, a logical 1. And if we reset, which means the same as clear, then the output Q is logic 0. Okay, so S represents set, R is reset, clear, reset means exactly the same thing. Okay. So we have two flip-flops that we can use to make an SC flip-flop. One is utilizing cross-connected NOR gates. So this is what we see at the circuit on the left, and so if we use cross-connected NOR gates, then we have active high inputs. So this is the actual circuit internally. This is the standard schematic symbol, so either one of these is valid, they're both equivalent. Active high means there's no bubble on the set here or the clear here. Okay, so that's how we know they're active high. There's no bubbles at S or C. Okay, so if they're active high, that means if we want to make the output logic 1, we want to set the flip-flop. So make the set equal to logic 1, clear is logic 0, Q is high, Q is the output. They provide not Q, which is just the inverse of Q, just as a convenience. If you need it, good. If you don't, leave it. Doesn't matter. Okay, but the output Q is always the output. Okay, that we're referring to. Then the mode is reset, or clear. If we make the clear and the reset both low, that means no change hold. So Q will stay at its prior logic level, whether high or low. Okay, do not make S and C 1 at the same time, which means you're telling the flip-flop Q to be high and low at the same time. That's an unpredictable situation, so that's an invalid state, so we don't want to use that. The SC flip-flop can also be constructed using cross-connected NAND gates. And if it's formed using cross-connected, sorry, that was one of my cats just jumping around on the window. The flip-flop is active low. So we have active low on set, a bubble, and active low on clear, it's a bubble. Okay, operation is exactly the same, but with the opposite logic levels. So if we're going to set the flip-flop, clear is going to be 1, set is going to be 0, output is going to be 1, which means set, so that's set mode. Okay, so logic 0 to activate the input. If you want to reset the flip-flop, that's the mode. Output Q is low, make set high to disable it, make clear low to enable it. And if we want to hold the output Q at its previous state, so this is the hold or no change, okay, mode, then clear and set are both high. Again, don't activate, which in this case means logic 0, both inputs, because the output Q, no idea what it's going to do. Okay, so once again, so the set clear flip-flop is exactly the same as the set reset, just little different terminology. Clear and reset mean the same thing, i.e. output Q is low. If we want to have active low inputs, then we make the circuit, the flip-flop, using NAND gates. If we want active high inputs, then we use NOR gates. Okay, and it's just that simple. Okay, next bit, latches. Latches are used to capture and store or hold data. Okay. This is called the gated latch. This is the internal circuitry here, the schematic symbol. Okay, so basically the gated latch behaves, if you just pretend that isn't there, like an active high input set reset flip-flop, which we just looked at. Okay, the only difference is with the enable, if you want the flip-flop to function, to respond to inputs, make the enable logic 1. Okay, so the flip-flop will operate normally only when En equals 1. If you tie En low, then, just down here, then the inputs S and R have no effect, and Q will just hold its prior logic level. Okay, gated latch. So this is edge activated, and we know in this case it's rising edge. This means it's edge activated. This is the clock, and its rising edge means it responds to a 0 to 1 transition because there's no bubble here. Okay, right? So you can read that note there. All right, we have a single input D and an output Q. So on the rising clock edge, the logic level on D is passed through to Q. And you can see then here, just sort of summarize the operation, that when D is logic 0, set is 0, clear, look at the inverter, clear is 1, Q is 0, the same as D. If D is then high, S is 1, clear is low, look at the inverter, Q is 1. So whatever is on D is passed to Q at the rising clock edge. Okay, and these could come falling edge activated as well. Operation would be exactly the same. Okay, JK flip-flops. So JK flip-flops, they're a little different. We're going to use these to build our counters. So it has a single output Q. J stands for jam. J is like set. If we activate the J, we want to make Q equal to logic 1. Okay. If we activate the K, K is like clear, reset or clear, Q is logic 0. Okay. And this particular one is falling edge activated clock. Note the bubble. Okay. They also come in a rising edge activated clock version. Okay. So basically, J and K respond on, in this case, on the falling or the 1 to 0 transition of the clock edge. Okay, here's the truth table. So don't worry about the QN plus 1. It's just something I often use just as a reminder that the flip-flop I'm talking about or considering, it's edge activated versus synchronous, which means the output is synchronized to the clock, which also is edge activated. Anyway, just confused you there. Sorry. So don't worry about that. That's still output Q. So if we set the J low, the K high, we're clearing the flip-flop. Q is low. If we set the J high, clear low. We're setting the flip-flop, Q is high. J and K both low, means no change hold its prior state. Okay, so if this was a 0, the previous state, this would be low, but in this case we had set it, so it was 1, so we're going to hold at 1. Now 1, 1 does not produce an invalid state, okay? It produces the toggle mode. So when we're doing our counters, the flip-flop will be in toggle mode, which means every time we hit it with a clock edge, then the output will toggle 0, 1, 0, 1, 0, 1. Okay, so this is the mode that we're going to use for counters, which I have a little note down here on that. Okay, JK flip-flop with asynchronous inputs. So this is exactly like the 74 LS76 JK flip-flop, which is what we're going to be using to build our counter circuits. So if we have asynchronous inputs here, and they can be active high or low, in this case they're active low. Low is more common. Okay. If we're not going to use these, which is normally going to be the case, well, maybe not normally, but often we're not going to use these, tie them high to disable them. Do not leave them floating. Okay, notice my note. Okay, so if we tie these high, tie this high, then J and K operates just as exactly the way it was on the previous slide. Notice the clock is falling edge, 1 to 0 transition activated. It could very well be rising edge, but in this case it's falling edge. If we activate the set or the clear, don't do so at the same time. You'll put the flip-flop in an invalid condition. Then whatever is activated here. So if we were to make the set low and the clear high, Q will go to logic 1 immediately and stay there, irregardless of what J and K and the clock are doing. Conversely, if we made the set high and the clear low, Q will be low, irregardless of what's going on here. So the asynchronous inputs override the synchronous inputs, the J and the K, which are tied to the clock. Okay, and that's the end. Thank you for watching, and I hope you found this, if not informative, maybe a little bit entertaining, but hopefully a little bit of both, and we'll see you soon. Okay, cheers, bye-bye.